Okay, so the first thing we were going to do today was to finish out the handout. And the handout, the one remaining problem, which I think is the function is it 3x plus 2 or 2x plus 3? Yeah. So what I want you to find is the derivative f prime of x. The answer's 3. Okay, I'll give you we go ahead and finish that. It shouldn't take you that long, but just look at your other examples. So today is apparently breakfast day. Yes, which I didn't know until somebody my boss reminded me, oh, is it breakfast today? And I go, I don't know. But Mr. Graham did send me a reminder. So that means at 8:50 we'll finish and you'll go over to the Mumaw Center. I have to go to Rockbridge, so I won't be able to partake, which is probably good after eating too much over Labor Day weekend. Remember, there's a test on Thursday. I have sent you the review link, and you'll have, it's not that super long a test, so I mean 50 minutes should be plenty, but I'm going to give you an hour and 45 minutes, so you don't have to worry about time. It's the easiest of the tests, which I guess if you find it hard, then it's time to panic. Not panic, but regroup. And it's just chapter 1. So how many people watched the game on Sunday night? A few? Yeah. I don't know here's my comments. Our defensive line couldn't put any pressure on the quarterback after the first few plays. It's like, okay, yep, let me look around here. Yeah, there's somebody there. Oh yeah, they're still there. Okay. Yeah, that was terrible. Thank goodness we have a good quarterback. By the way, we did win, which I was expecting us to lose, so I did wear my shirt before the game. I'm not just a guy that wears it after we win, but So there you go. It's probably seemed too easy, right? Because after the other ones, you're like, oh, this is hard. So we substitute x plus delta x in for x. So we have f of x plus delta x and f of x, and we subtract f of x from f of x plus delta x. We simplify, we divide out, because we're dealing with a polynomial, so that's what we do with polynomials. So the delta x's cancel out, we just have a constant. The limit of a constant is just the constant. So anyway, there we go. So you can turn those in after class. The two other examples I want to work on it before we move on to the next section is, this is problem 27. Find an equation for the tangent line. Graph the equation and the tangent line. Use the derivative function of the graph program to confirm your results. Okay, maybe you might not have that available, but I'll show you how that works. The graphing program that I have on Blackboard does have the derivative function of it capability. And we've already worked through this, so I'm not, if you get to these points, if I've assigned any problems that are just asking for tangent lines, you probably can just use what we know. We came up with the formula. We haven't officially defined it, but I've already done that, so I'm not going to do it again. So what we proved earlier was that in the general case that the derivative of x cubed is 3x squared. Okay. So what they want us to do is find the equation for the tangent line and to plot both the equation and the tangent line to prove that this actually is tangent to the curve at x equals 2. So we're doing this for a specific value of x. So we need two things. We need the value of the function at x equals 2, and we also need the value of the derivative. We need the value of the function because we need a point and a slope to figure out the equation of the tangent line. So f of 2 is the original function, so that's 2 cubed. So that means f of 2 is 8. So we could say at x equals 2, y equals 8, or we could say a point on the graph is 2, 8. These are all the same way of saying the same thing. So we have a point. Now we need the slope of the tangent line. So the derivative f prime of 2 is just 3 times 2 squared, which is 12. So that's the slope of the tangent line at this point. Slope of tangent line at x equals 2. So now we need the equation of the line. So we use the point slope form of the linear equation, which is y minus y1 equals m times x minus x1. In this case, our point is 2, 8. That's the point we're trying to find the tangent line. And m, where is it? Is 12. So now we just plug those in there. So y minus y1, which is 8, times m, which is 12, equals 12 times x minus x1, which is 2. And we multiply out the right-hand side. So we get 12x minus 24. Add 8 to both sides. And we get y is equal to 12x minus 16. So that's the equation for the tangent line. Because it has the slope of the tangent line and it goes through the point. So equation of tangent line to f of x equals x cubed at x equals 2. So that's all there is to do it. And so now we're going to plot the thing. So we'll put the original function, which is x cubed, in there, x cubed, and the equation was 12x minus 16. And if I did this right, and I remembered what I just did, we should see that the blue curve, which is the tangent line, should be tangent to the red curve, which is the original function. So I've got to zoom out a little bit here, but you can see it is. So that's the value. You can see the value of the function at x equals 2 is 2 cubed, which is 8. And the blue curve, if we zoom in on this little point of interest, you can see that no matter how close I zoom in, that the red curve is always on the top side. It only intersects at one point, which is 2, so we know we did it right. Okay, so that's how those problems work. What else? Did they ask us to do anything else? Oh, use the derivative function. Okay, let me show you how that works. So to do the derivative of a function in this particular program, what you do is you put d and then the function. So if you want the function that's the derivative of x cubed, which should be 3x squared. What I do when I do this, I should get a parabola. So let me go back to standard thing here. So you can see the green line was the third thing I did, and so this is the derivative of the green curve is the derivative of the red curve. And you can see at x equals 2, the derivative equals 12. So I put my cursor right here, it's 12, which is what I found out doing analytically, is that the value of the derivative at x equals 2 equals 12, or 2 plugged into the equation 3x squared. I don't think yours does that on your calculator, so that's one thing. Okay. So now we have problem 35, which says find the equation of the line that is tangent to the graph and parallel to the given line. So this is a little more obscure. So what we do is we're going to take the derivative of this function, which we've already done again previously, so I'm not going to redo it. And you find the slope of this line, which is the line you're trying to find, the tangent line that's parallel to you're trying to find the tangent line of this curve that's parallel to this curve. So probably the best thing to do is to plot it out and just try to see what the heck they're talking about. So I know what they're talking about, but you may not know what they're talking about. So let's just plot those two functions. So you got the square root of x is the function, and it says make it parallel to this equation. So if we solve that, put that in slope-intercept form, you get 2y is equal to 6 minus x. So I just move these to the other side and then divide by 2. So I'll get y equals negative 1/2 x plus 3. I switch the order there. So if you divide everything by 2, you get 6 divided by 2 is 3, and negative 1 divided by 2 is negative 1/2. So that's the equation. So let's plot that. So it's negative 1/2 x plus 3, negative 1/2 times x plus 3. So we'll graph that. And let me zoom out a little bit, because originally what would bother you about this curve if you saw that without looking at any point, without expanding the graph? Well, the blue curve has a negative slope, but any tangent line to that curve has to have, right now it has to have a positive slope unless it curves around, which it's not going to because it's the square root of x. So now the question is, did I do something wrong? Oh, it's 1 over the square root of x. Okay, there we go. So that's why when you see something that looks fishy, you're like, oh, what's wrong? But yeah, see, this is negative slope. All the tangent lines are going to be positive slope. So I knew either I wasn't looking at the graph enough or I'd done something wrong. So apparently I had done something wrong. So let's fix that. So it's 1 divided by the square root of x. Let's see what that looks like. Okay, so now I can see, maybe about right here, the tangent line is going to be parallel to the blue curve. So there is a solution here somewhere or another. Looks like about x equals 1, but I don't know yet. So we kind of do the same thing except going at it from different directions. Here's the slope that we're trying to find. Basically, we're going to take the derivative of this, which we did last week. So f prime was equal to negative 1 over 2 times x to the 3/2 power. Was that one that we did on your handout? Or was it one I did? I think it was one you did on your handout. I think that's right. You get the negative 1/2 because this is x to the minus 1/2 power. So you get the exponent of negative 1/2. You decrease the exponent by 1, which gives you negative 3/2. Move that to the denominator. So that's the equation for the tangent line. So the question is, what is the value of x such that the slope is negative 1/2? What value of x is the tangent line have the same slope as the curve here? So all you have to do is just say negative 1/2 equals negative 1/2 times 1 over x cubed, to the 3/2 power. So this number is the slope that I'm trying to match. And this is the equation for the tangent line saying what value of x does that happen at? Well, you can see that I've got negative 1/2 on both sides. So I get simplified to that. Multiply both sides by x to the 3/2. I get that. And then multiply both sides by x to the 2/3. So if I get x to the 3/2 times x to the 2/3, wait a second. No, that's not what I want to do. I'm just going to raise it to the 2/3 power. So I'll take x to the 3/2 raised to the 2/3 power and 1 to the 2/3 power. So I'm doing the same thing on both sides. I'm taking it to the 2/3 power. And when you have an exponent raised to another exponent, you multiply the exponents together. So 3/2 times 2/3 is 1. That's the whole purpose of doing that. So you get x to the first power. And 1 to the 2/3 power is 1. And so the answer is 1, which is what I thought it was going to be. So, so what that's saying is that at x equals 1, the slope of the tangent line to f of x equals 1 over the square root of x is negative 1/2, which is the same as x plus 2y minus 6 equals 0. So it has the slope of the tangent line at x equals 1 has the same slope as the curve that they were asking about. And we could prove that by figuring out what is the equation of the tangent line, which they didn't ask us to, well, they did actually, find an equation of the line that is tangent to the graph. Yep. So, so I need to still find the equation of the tangent line. So now I kind of do what I just did before. I have the value of the function. I have the value x. I need what f of x is, which turns out, if I want to then find out what is f of 1, it's 1 over the square root of 1. So I just plug that in my equation, which is 1. And you can see that if I go back to the graph at x equals 1, y equals 1. Okay. So now I have the slope, which is negative 1/2, and I have the point. So I'll say, okay, I'll say it at, well, no, all I'll say is, so now what I need to do is find the line with the coordinate 1, 1, which is the point on the curve that I'm trying to find the tangent line, with the coordinate 1, 1 and slope of negative 1/2. So I just stick that into the point slope form of the linear equation again, just like it did previously. So you get y minus y1, which is 1. So here we have x1, y1. So you get y minus y1 is equal to m, the slope, negative 1/2, times x minus x1. x1 is 1. So we multiply all that stuff out. So you get negative 1/2 times x, which is negative 1/2 x. Negative 1/2 times negative 1 is positive 1/2. We add 1 to both sides to solve for y. So you get y is equal to negative 1/2 x plus 3/2. So that's the equation of the tangent line to the curve. And now if I plot that curve, it should be two things. It'll be tangent to the red curve, but also parallel to the other curve. Negative 1/2 plus 3/2. So if I do that, negative 1/2 times x plus 3/2, and I plot that, and there it is. That's the green curve. So let me review what I've just done. First thing I did is I found the slope of the blue curve. They said that they wanted you to find the equation for the tangent line to the red curve that had the same slope as the blue curve. So I took the slope that I calculated from the blue curve and set that equal to the equation for the derivative of the red curve. And then I set what I did was, well, first I found the derivative, which I'd already done before, and I set the slope of the blue curve equal to the derivative of the red curve. And I said, okay, what values of x does that happen? So I solved this equation algebraically for x and found out the x value where that happened was 1. And then I plugged 1 into my function to find out what the corresponding y value was, and y turned out to be 1. So that's the point at where the curve I'm looking for is tangent to the original curve. But they asked for the equation of the line, not just the point that the line went through. So I had to find the equation of the line, the tangent line. I had to take this point that I knew and the slope that I know, wherever that is on the next page. So I took that point and the slope, found out the equation of the tangent line, which was that, and then I plotted it. And I found out that I did it correctly, because you can see that if I zoom in here, that the green curve is parallel to the blue curve. They both have a slope of negative 1/2. The green curve is tangent to the red curve at x equals 1, and so everything's perfect. Everything's wonderful. So that's what they're looking for when you might have a problem like that in homework too. Okay, now I already assigned these, so anybody have any questions on any of that? Okay. Section 2 is pretty short. Section 3 gets a little more exciting, and Section 4 gets the most exciting. So there are a few things that you can come up with these theorems or rules for differentiation based on what we learned in Section 1, or you can prove that these are true for all cases. And we've already actually proved the first one is somewhat trivial, but it's important. The one we just looked at was, the one that you did for your handout was, if the function is 3x plus 2, we found out that the derivative was equal to 3, just 3. So the derivative of 3x is 3, and the derivative of 2 is, that's a question for you guys. What's the derivative of 2? You're like, I don't see it. It's because it's 0, right? So when you take the derivative of a constant, it's 0, and therefore you don't ever, you can put it in there. But so the first rule is the derivative of a constant. So c is a constant. So the derivative of 6 is 0. The derivative of 0 is 0. The derivative of negative 26,729 is 0. And it makes sense because if the function f of x is a constant, that means it's a horizontal line. What's the slope of a horizontal line? It's 0. So it agrees with what our graphical understanding of derivative is. So, like over here, when you have an expression that has a constant in it, when you take the derivative, the constant goes to 0. You can just drop it. You don't have to say it's equal to 0. You can just leave it out. Okay. Power rule for differentiation. We kind of came up with that, and actually I'm not sure if it's this section or the next section that they officially introduced this, but I'm going to do it this time. So it says if you have a function equal x to the n, x is your variable, n is a number, and so if f of x equals x to the n, then the derivative of that polynomial is equal to n, the exponent, times x to the n minus 1, except for n equals 0. It doesn't work, but it turns out it works for every other number. Positive, negative, whole number, integer, rational number, irrational number. I don't think it works for imaginary numbers, but pretty much every number except 0. And we've seen that. We saw that, even in the 3x plus 2. In that case, 3x plus 2, the exponent is 1, x to the first power. So when you subtract 1 from 1, you get 0. X to the 0 is 1. So let me explain what I just said there. So if you had f of x equals x, it still works for that because that's x to the first power. So n equals 1. So the derivative of this function is 1, the exponent, times x to the 1 minus 1, which is 1 times x to the 0. But anything raised to the 0 power is 1, so you get 1. So the derivative of the variable is just 1. Derivative of x is 1. If I did, if f of x equals x squared, we just did this, f prime of x is going to be equal to 2, the exponent, times x to the 2 minus 1, which is 2 times x to the first power, which is just 2x. When you have numbers other than 1 or 0, 1 or 2 is the exponent, it's actually more straightforward because here you have to recognize that anything raised to the 0 power is 1, even if it's unknown. It's a variable. And then here, x to the first power is just x. But if I had x, let's say f of x equals x to the 100th power, f prime of x is going to be 100 times x to the 100 minus 1, which is 100 times x to the 99th power. I didn't have to, this one I simplified and said that x to the first power was just x. Actually, here's a little insight. Why is that? I'm going to open up my my notes from last time. So you got when we did x cubed, that went too fast here. Got whiplash. Huh. I thought it did x cubed somewhere. I don't know where it is. X squared, x cubed. Let me just show you. I know it did x cubed. Where is it? Oh, there we go. Yeah, here it is. This is what I'm looking for. Notice when we did x cubed, you had this term, which was the second term in the series, or the second term in the expansion. So we had this 3x squared times delta x, but when we divide it by delta x, it's the only term that doesn't go to 0 when delta x goes to 0. This term goes to 0 because you have delta x times, so this goes 0 times that, which 0 times anything is 0. Here you have 0 squared. So, so the only term that remains is this first one. So if we were now to go back here to what we were just looking at, which is this one, and let's look at the case of 100, f to the 100th power. Don't write down what's on the left-hand side. So if you had f of x equals x to the 100th power, if you were to write this out as f of x plus delta x, you would have x plus delta x to the 100th power. And we know that that is going to be equal to x to the 100th power plus 100 times x to the 99th power times delta x. And I don't know what the next term is. It's not important. This term gets canceled out by f of x. So f of x is 100, x to the 100. So when I subtract f of x from f of x plus delta x, these cancel out. This term is the only one that's going to have delta x. All the other 98 terms are going to have delta x squared, delta x cubed, delta x to the 4th, and when I simplify it, all those 98 remaining terms are going to have at least delta x in them once I simplify it. The only term that's left that once I cancel out or divide out the delta x, the only term that's not going to have delta x in is this one, and that's the only one remaining. And that's why the rule works, because the derivative of x to the 100th is 100 times x to the 99th. And that's why the whole thing, that's kind of the underpinnings of the whole thing. It's the first term in the expansion of that thing to the 100th, or to whatever power it is. Okay. I skipped over this because I did ones very similar to it. Also, if you can use the power rule for simple expressions where you have something raised to a power in the denominator. So we can't use it directly, but we have to, first thing you have to do, so what they're doing here is they're saying f of x equals 1 over x to the 4th. So what is f prime of x, question mark, using this formula? Well, the formula says that it has to be x to the n. This is 1 over x to the n. So the first thing we do is we rewrite f of x. So instead of f of x being 1 over x to the 4th, it's x to the minus 4th. Now once you rewrite it, it fits into the form of the formula. So now what we do is we'll say n is equal to negative 4. So n minus 1, which is the new exponent, is going to be negative 4 minus 1, which is negative 5. The mistake people make is they forget they have to rewrite this as x to the minus 4th power, and they'll say, oh, it's 1 over the derivative of 1 over x to the 4th is something like 1 over x to the 3rd power. I'm going to subtract 1 from the exponent because that's the rule, but you can't use the rule until you rewrite it in the form where it's x to the n, not 1 over x to the n. There is no formula for 1 over x to the n. There is a formula for x to the n. So now that it's in the x to the n, I can identify n, and I can make the appropriate subtraction. So I'm going to subtract 1 from a negative number, which makes it more negative. So then what happens is I can just say that f prime of x is going to be n times x to the n minus 1. And then you rewrite it again, because we don't like to leave things with negative exponents in the answer. So then we go back and we say, yeah, f prime of x is this, but it's really negative 4 over x to the 5th power. And that's the answer. Don't leave it in that form. Don't leave me this way. What's that song? Who sings that? Don't leave me this way. Don't. Anybody recognize that song? I'll have to do some research on that. I'm always thinking of songs that go along with things I say. Okay. I'm going to research. Let's do a quick research. Don't leave me this way. So you got to rewrite it so that it's a positive exponent. Okay. I was watching this video I made for my math for the liberal arts class, and I don't know how, and it was the song, I think it was Three Dog Night. It was One is the Loneliest Number. Anybody heard of that one? One is the loneliest number since. Okay. So that's what you do when you have a positive exponent in the denominator. You can also use the formula for, yeah, there's my annoying sound there. Let's get rid of that. You can also use the formula for fractional exponents. So again, you would rewrite first, just like you rewrote f of x. So we rewrite f of x as f of x equals x to the 1/2 power. So in that case, n equals 1/2, n minus 1 equals 1/2 minus 1, which is negative 1/2. So using the formula, f prime of x equals n times x to the n minus 1. And again, we don't leave it this way. Yeah, don't leave me this way. So what you do is you rewrite. You do two things in this case. First is you move the exponent to the denominator, make it positive, and then you change the square root. I mean, x to the 1/2 power into a square root, and then you get the answer. When we actually derived this thing, which I think I derived this, I left it as a square root the whole time. I didn't change it to x to the 1/2. But to be able to use the formula, you have to do that. You have to rewrite it and then rewrite it again. Now, usually the only time I rewrite it like this and don't leave it as just a fractional exponent is if it's the square root. If it's something like, x to the 3/2 power, I usually just leave it as x to the 3/2 power, leave alone. Is there a song to go with that? I don't know. Leave alone. Okay. The only one you don't is when you have x to the 1/2 power. Make it back as a square root. I mean, you could rewrite this as the what is it? The square root of x cubed, I guess. The reality is if you actually evaluate this on your calculator, you're going to do that. So, oh, what happened there? It went crazy. Okay, moving on. There's the constant multiple rule. So we've talked about what is the derivative of just a constant. If you have a function multiplied by a constant, the uh, the derivative is just the constant times the derivative of the function. So the constant, only thing the constant does is scale the derivative by the same amount that the original function was scaled by. So if the original function was x squared, you multiply by 5, you just make everything 5 times larger, and so the impact on the derivative is the same thing. So let's just use this example here, 5x squared. So I'm going to move this over a little bit. So let me just call g of x equal to x squared. So f of x is just 5 times g of x. So if I said what is, and also let's say h of x, oh no, g of x is x squared, that's good. So if I ask you what's g prime of x, what's the derivative of this function? It's just 2 times x to the first power, which is just x. So this becomes 2x. So when you look at f prime of x here, all we do is we take the multiplier 5 and multiply by g of prime of x, which is the function without the multiplier. So that's just 5 times g prime of x, which is 2x, which is 10x. Now, what you'll end up doing once in a week or so, is when you take the derivative of this, you'll say, oh, I'm not going to go to all this trouble. I'm just going to say the derivative is I take the exponent 2 multiplied by the constant in front, which is 10, which is what I get here. I won't go to all the trouble. And I reduce the exponent by 1. So I get 2 times 5, which is 10, times x. So let me give you another example of that. So let's say you have, let's say f of x equals 12x cubed. Then f prime of x is equal to 36x squared. So I just take 3 times 12, which is 36, times x to the second power. So let's do another one. F of x equals 1/2 x to the fourth. And let's find somebody to ask the question here. Elias, what's the derivative of 1/2 x to the fourth?
2x cubed.
Yes, very good. So what he did is he took 4 times a half, which is 2, and then x to the third power. Let's do one more here. F of x equals 15x to the fifth. So f prime of x. So Daniel, what's the derivative? See how good you are multiplying in your head. You can use your calculator. Yeah. Okay. So we're using the constant multiplier rule there. We're kind of making it we're combining it into one step. Then we have the sum and difference rules. We actually we did that when we did the 3x plus 2 situation. In that case, the derivative of 3x was 3, the derivative of 2 was 0. So if you have functions that are added together, then all you do is you take the derivatives of the functions by themselves. So it's saying the derivative of the sum of two functions is the sum of the derivatives of the individual functions. And if it's subtracted, it's the same thing. So it says derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x, which is just f prime times g prime. So we'll do one quick example. You got donuts coming up here, so let's. So the usual case is like a polynomial. So if I had x to the fourth plus 3x cubed, what I would do is the derivative of this would just be the derivative of each one separately and add them together. So the derivative of x to the fourth would be 4x cubed, and the derivative of 3x cubed be 9x squared. That's it, okay? That's the addition and difference, it's the sum and difference rules. You just treat them like they're individual derivatives. There's no special thing you do because they're added together. What we'll find out in the next section is that if we took the derivative with respect to x of the product of two functions, this is where your intuition would be wrong. What you might think is, don't write this down because this is wrong, you might think it's f of prime of x times g prime of x. That's not true. Okay, so you can't do that with multiplication or division. You can do it with addition or subtraction. We'll tell you what, we'll work through that when we get to the next section. But I'm going to go ahead and assign the, well, I'll wait till, well, no, it's Tuesday, so I'm going to go ahead and sign this today. So there's a lot of problems, but they're all pretty easy because they're just using the power rule, which you could do, you could do a problem in 10 seconds. So it looks like a lot, but it's not that much. I think some of these here you may have to find the equation of the tangent line, but we know how to do that now. So after you fill up your belly with donuts, oh, I was going to try try my Scottish accent here. What's that guy's name? Not Shrek. It's the same guy. It's the guy that does Austin Powers. Fat. Beep. Yeah, think of that, Mr. Fatso.